Entropy is one of the most confusing and badly explained ideas in all of science. If you have heard the word before, you probably agree, at least that it feels confusing. That confusion has several causes, and many of them are historical. 19th century physicists picked a name and a notation that stuck before anyone knew about atoms, and textbooks kept the old vocabulary while the meaning moved underneath. People still say entropy means disorder. People still say it means chaos. People still say nobody really understands it. All of that is a sign that the word survived longer than the picture that should come with it. My goal in this video is not to walk you through that entire archive. My goal is to show you, in the simplest way possible, that entropy is a statistical quantity, and that once you accept that definition, the second law of thermodynamics follows almost automatically. That is the thread holding this story together. Counting first, then the law, then why the world only runs one way at the scale you actually live in. We will start with a grid of coins small enough to fit on a table. We will end with the universe. The same logic travels the whole distance. So what do we mean by statistical? Before anything else, entropy is not something you can touch. It is not a physical substance you can feel or bottle. When we say entropy is statistical, we mean it counts the number of ways you can arrange the atoms of a substance without changing what you observe. Temperature, pressure, volume, the macroscopic story. The result you measure is a statistical result. I will show you how that counting works with an example you can picture, and then we will scale it until it explains your coffee, your broken cups, and the universe. If you stay with the count, the rest is bookkeeping. Suppose we have 36 identical coins. Each coin has a blue face and a red face. Arrange them in a 6x6 square. Start with every coin showing blue. If I asked how many different ways you can produce the picture all blue, the answer is one. There is only one configuration. Every coin must show blue. We call that picture the macrostate, all blue. Do not worry about the jargon yet. That macrostate has only one way to occur. That way is what we call a microstate, a specific configuration of the system. We call the number of configuration. Here, W equals 1. Now flip exactly one coin to red. How many configurations give you 1 red and 35 blue? 36. The red coin could be any of the 36 positions. If that is not obvious, think about it this way. We can place the red coin in any slot and the rest stay blue. Still 35 blue, 1 red. The macrostate 1 red and 35 blue has 36 microstates. W equals 36. 2 red, 34 blue. How many ways? The combination formula gives 636. W equals 636. Still small enough to picture. Still small enough to write on screen if you had patience. But watch what happens when you add one more red. 3 red, 33 blue jumps to 7,140. 1 red coin added, and W multiplied by more than 10. That is the combinatorial cliff hiding inside every thermodynamics textbook. There is a symmetry worth naming. All blue and all red both sit at the edges of the board with W equals 1. Perfect order on one color is rare for the same reason. Perfect order on the other is rare. The difference is history. You start all blue because I said so. A gas starts in a corner because someone or something put it there. Once released, the system wanders toward the middle. For the same reason, a drunk walker in a large city spends more time in busy districts than in one specific doorway. Not because the doorway is forbidden, because almost all paths pass through the crowd. Next case. 3 coins red, 33 blue. How many ways? Run the combination count, and you get 7,140. The macrostate 3 red and 33 blue has 7,140 microstates. W equals 7,140. Let us keep going because the jump is the lesson. 10 red, 26 blue. The combination gives 254,186,856 configuration. W equals 254,186,856. That number is already exhausting. I cannot show it on screen the way I showed 7,140. There literally are not enough pixels on a full HD monitor at 1920 by 1080 to write the whole thing. Every pixel would need to be a digit, and the monitor would still run out of room. Between 10 and 18 red, the curve does not politely rise. It explodes. 5 red and 31 blue already sits near 376,000. 15 red and 21 blue sits near 8 million, the middle of the distribution. Where red and blue are most evenly mixed is where W peak. That peak is not an accident of coins. It is the shape of combinatorics itself. Macrostates that look balanced to your eye are macrostates that can be built in the most different ways at the microscopic level. Thermodynamics lives on that peak. Push to 18 red and 18 blue, half and half, the most mixed macrostate on the grid. You get about 9,075,000,000 configurations. If you showed one configuration per second, this video would need 300 years to get through them all. And that is still a toy with 36 coins. If you flipped coins at random, no plan, just toss, you would not land on all blue very often. You would not land on 1818 every time either, but you would land near the middle far more often than near the edges. All blue is one ticket in a lottery, with 9 billion tickets at the peak. That is the statistical heart of the second law, hiding inside a children's puzzle. Random flips drift toward mixed because mixed owns almost all of the tickets. Notice what the coin board is really doing. We did not change the coins themselves. We changed how many microstates share the same macroscopic description. Macrostates that look more mixed to your eye usually own larger W than macrostates that look tidy. That is why the word disorder keeps surviving in pop science. A shuffled deck has more microstates than a sorted deck. A broken cup has more microstates than an intact cup. But disorder is the metaphor. W is the math. The growth is not linear. It is combinatorial, close to exponential as you move toward the middle of the grid. From 1818 onward, the counts are so large that display itself becomes absurd. That absurdity is not a party trick. It is the reason you cannot do thermodynamics by listing atoms one by one. If you plotted W against the number of red coins, the curve would look like a hill. Low at the edges, high in the center. Flip coins at random and you sample that hill. You spend almost all your time on the slopes near the top, not on the single peak pixel of all blue. Real gases sample their hill the same way. Pressure and temperature are readings from the slope. Equilibrium is living on the slope where further wandering does not change the macroscopic readout much. The coin hill is two-dimensional theater for a law that runs in 10 to the 23rd dimensions in a box of air. Now imagine a gas with 10 to the 21st atom. That is why thermodynamics is statistical. You cannot list the arrangements. You cannot simulate them on any machine that will ever exist. You can still reason about them the same way we reasoned about 36 coins. Ask which macrostates own almost all of water, and ask which macrostates own almost none. Thermodynamics is statistical because the count forces it to be. You do not follow every molecule. You follow what is typical. Typical for large systems means what the overwhelming majority of microstates allow. Avogadro's number, about 6 times 10 to the 23rd particles per mole, is the scale where the coin board stops being a metaphor and becomes a laboratory fact. A mole of gas at room temperature carries that many molecules in a volume you can hold in 2 hands. Each molecule updates its position and velocity billions of times per second. The macrostate pressure and temperature you read on a gauge is the crowd average of an unimaginable parade. Engineers do not need the parade. They need the law the parade obeys. That law is the second law. And we are 2/3 of the way to stating it honestly once we admit we only ever see crowd. We define entropy exactly the way we started. Entropy is a number that counts the total possible ways the atoms of an object can be arranged while the macroscopic picture stays the same. In the coin example, entropy tracks W. Think now about the coffee mug you drink when you wake up. The number of atoms in that coffee is gigantic, on the order of 10 to the 21st, but still finite. The number of ways those atoms can rearrange while the coffee still looks like coffee to you is also finite. And also gigantic. Every formula from here is just a way of handling W when the number has 21 zeros attached. Hold that mug in your hand for a second. You see one color, one temperature to the touch, one smell. Your senses report a macrostate. Underneath, water molecules slam into each other billions of times per second. Each collision swaps a little energy. Each swap is a step between microstates that all look like coffee to you. You never see the steps. You see the average. Thermodynamics was invented because humans see averages and need a law for averages. The coin grid taught you what an average hides. The mug is where the hiding becomes life-sized. The first people to think about entropy in these statistical terms in the second half of the 19th century were Ludwig Boltzmann and Josiah Willard Gibbs. They built on kinetic theory. The idea that gas pressure and temperature come from countless collisions, developed by James Clerk Maxwell and others. Maxwell derived how molecular speeds distribute at a given temperature. The Maxwell-Boltzmann distribution is still the first thing you meet in a statistical mechanics course. Boltzmann wrote how those distributions change when molecules collide. Gibbs packaged the framework for chemists and engineers working with reactions and equilibria, giving them a language for free energy and chemical potential that still runs modern chemistry. Maxwell, Boltzmann, and Gibbs are considered the founders of statistical mechanics. The coin grid is the toy version of what they did for real gases. Before atoms were accepted as real, thermodynamics already worked. Carnot and Clausius measured heat and work without picturing molecule. After atoms won the argument, Boltzmann asked what heat meant at the bottom. Heat is not a fluid called caloric. Heat is energy shared among many modes of motion. When that sharing spreads, W grows. The 19th century fought that idea bitterly. Atoms were still controversial when Boltzmann published. Some of his opponents never accepted statistical mechanics in their lifetimes. The coin board would have helped. You do not need to see molecules to see why mixed owns more W than sorted. Gibbs took the next step that chemists needed. Never. Reactions that look reversible in a beaker, salt-dissolving, acid-neutralizing base, sit in equilibrium when forward and backward rates balance. Equilibrium is not zero entropy. It is the maximum entropy available at fixed energy and volume. Gibbs' free energy tells you which direction a reaction runs when pressure and temperature are fixed. Every time a battery dies or rust spreads on iron, a Gibbs calculation somewhere would have predicted the drift toward higher total. The coin board is crude. Gibbs is the coin board with chemistry homework attached. Boltzmann asked the question that ties the grid to your kitchen. If heat is molecular motion, why does hot flow to cold and never the reverse? Why does perfume spread through a room and never unspread? His answer was not a new force. After mixing, the macrostate almost always sits on a larger W than before, more ways to hide the same total energy when it is spread across more modes. Hot and cold separated is a low W macrostate. Lukewarm everywhere is a high W macrostate. The gas does not choose to spread. It wanders into the macrostate that owns almost all of the microstates. Temperature itself is a macroscopic readout of that wandering. When we say two objects are the same temperature, we mean their average energy per way of arranging energy is balanced. Put a cold spoon in hot soup and the spoon warms because energy flows until the combined system finds a partition with more total. The spoon never steals all the heat and leaves the soup frozen. The frozen soup and red-hot spoon split is a needle. Lukewarm dinner is the haystack. Picture two connected boxes with a divider. All gas on the left, vacuum on the right. Remove the divider. The gas expands. Why? Because the macrostate gas everywhere owns almost all of W, compared with the macrostate gas only on the left. The reverse. All gas spontaneously returning to one side is allowed by Newton in principle and buried by statistics in practice. That answer is the birth of the second law in microscopic language. Maxwell himself pushed the idea into a famous thought experiment. The demon seems to sort hot from cold without work. The resolution, worked out decades later, is that the demon pays entropy when it measures and forgets information. Sorting is never free. Every trick that looks like beating the second law smuggles a cost somewhere. Measurement, erasure, or contact with a reservoir. Maxwell's demon is not a loophole. It is a lesson that information and entropy travel together, but that is not the whole story yet. If you search Boltzmann entropy, you find S equals K times the natural logarithm of W. Or, if you travel to Vienna and visit Boltzmann's tomb in the Zentralfriedhof, the Central Cemetery, Group 14C, not far from Beethoven, you find the same formula carved above his bust. I said entropy tracks W. So why the logarithm and what is K? Here is why the logarithm appears. Go back to the coffee. Or better, 2 mugs of coffee. Call them mug 1 and mug 2. We can study entropy in each mug separately. Nothing stops us from treating the combined system as one object. Mug 1 has W1 microstates. W prograde mug 2 has W2. Combined, The number of ways to arrange all the atoms is W1 times W2 multiplication, because every arrangement in Mug 1 can pair with every arrangement in Mug 2. Imagine Mug 1 with 1,000 ways to arrange its atoms while still looking like coffee. Mug 2 with 1,000 ways. Together they do not have 2,000 ways, they have 1,000,000. Multiply again with the third mug, and you are at 1,000,000,000. Real mugs are not 1,000-state toys. Real mugs carry counts with 20 digits. Multiplication is how independent systems combine at the microscopic level. Clausius already had a microscopic entropy that added when you merge systems. Boltzmann needed a microscopic quantity that added the same way. The logarithm is the bridge. Now ask about energy. If we combined the two mugs, total energy would be the sum of the energies of each mug. Energy adds. Entropy should add too when we merge systems, but W multiplies. The logarithm fixes that. Log of W1 times W2 equals log W1 plus log W2. The log turns products into sums, so entropy behaves like energy on a balance sheet. That is not decoration. That is why the formula works in the same equations as the first law. The constant K is Boltzmann's constant, about 1.38 times 10 to the minus 23 joules per Kelvin. It gives entropy units of energy over temperature, joules per Kelvin, matching the format of the first law. Without K, you have a pure count. With K, you have a physical quantity you can plug into engines and refrigerators, the way you plug internal energy into calorimetry. Boltzmann did not publish S equals A log W in exactly those symbols. Max Planck put the formula into modern form around 1900 and named the constant after him. Planck later wrote that the logarithmic link between entropy and probability was first stated by Boltzmann in his kinetic theory of gases. How small is K? Small enough that everyday entropy changes look like ordinary numbers on a lab sheet. Heat a liter of water by 1 Kelvin and the entropy rise is on the order of a few joules per Kelvin. Tiny compared with the internal energy stored in the same liter, but exactly the increment Clausius would have measured before anyone knew about atoms. K is the conversion rate between counting and doing work. It is why the gravestone formula is not just poetry, it is engineering. Planck needed K when he fixed the ultraviolet catastrophe in 1900. Light emitted by hot objects could not be explained if energy were continuous at every scale. Quantizing oscillators required a constant linking average energy to temperature. That constant was K. Blackbody radiation, the birth of quantum mechanics, and the formula on Boltzmann's tomb all meet in the same hallway. Entropy was never a side quest. It was the door quantum theory walked through when classical physics ran out of counting tricks. If you type Boltzmann entropy into a search engine, you get S equals K times the natural logarithm of W. Earlier I said entropy tracks. So why the logarithm? Because W multiplies when systems combine, and entropy must add because K supplies units. Because Clausius and Carnot were already measuring a macroscopic quantity that climbed when heat spread, and Boltzmann showed that quantity was the logarithm of the count we started with on the coin board. 3 historical layers. 1 ledger. Visit that grave when you can. Group 14C in the Zentralfriedhof is a pilgrimage site for physicists the way Abbey Road is for Beatles fans. The bust looks tired because Boltzmann was tired. Years of fighting over atoms, years of defending statistics, years of depression while the establishment called his work unfinished. The formula outlasted the fight. Today, every chip in your phone relies on quantum mechanics that still uses K. The tomb is not nostalgia. It is a unit marker for the same count we did with 36 coin. Do not panic when people call entropy mysterious or say nobody understands it. That is false. Entropy is well understood. And once you see the count, it is even simple. The idea now is to use that concept where it matters most. The second law of thermodynamics. This law is central to almost everything around you, and it leads all the way to questions about the origin of the universe. In the first chapter of this course, we talked about energy and conservation. In an earlier video, we showed that energy is conserved, absolutely fundamental in all of physics. Now we ask, does entropy obey a similar fundamental rule? You already know the answer from the coin board. Energy balances. W does not sit still in an isolated box. The second law is what happens when you stop cheating with outside hands and let the grid evolve on its own. It does not, unlike energy. The second law of thermodynamics says the total entropy of an isolated system tends to increase as time passes. The consequences of that are surprising. But before we state the law with examples, we need one more piece: reversibility and irreversibility, because that piece is what connects counting to the one-way world you actually live in. In an earlier video in this series, we already established that energy conservation is absolute in physics. Energy cannot be created or destroyed, only moved and converted. A ball falling converts gravitational potential energy into kinetic energy. A battery converts chemical energy into electrical energy. The total stays on the books. Entropy plays by different rules. In an isolated system, entropy does not go down. It climbs toward the macro states that own almost all of W. That difference is why perpetual motion machines fail two different ways. A machine that creates energy from nothing violates the first law. A machine that converts a single hot reservoir into work forever violates the second. Patents for both still arrive in physics departments every year. The first kind is arithmetic fraud. The second kind is counting fraud. It pretends you can stay on a low W macro state while doing macroscopic work. Carnot proved the ceiling. Clausius named the climb. Boltzmann showed the climb is what happens when almost all microstates agree. Sadi Carnot, in 1824, asked a practical question about steam engines. How much work can you extract when heat flows from hot to cold? He proved perfect conversion of heat into work is impossible. Not because engineers were clumsy, but because nature charges a tax on rearrangement. Rudolf Clausius in the 1850s named that tax entropy and gave the second law its famous sentence, "The entropy of an isolated system tends to increase." He built the word from a Greek root tied to transformation. Energy is conserved. Entropy is not. That asymmetry is the drama every thermodynamics course tries to explain. Picture a Carnot engine in your head even if you never built one. Hot reservoir, cold reservoir, working fluid cycling through isothermal and adiabatic steps. The engine pulls heat from hot, dumps waste heat to cold, and delivers work on the shaft. Carnot proved no engine operating between the same two temperatures can beat that cycle's efficiency. The waste heat is not optional. It is the price of running a cycle at all. Clausius read that price as entropy production. Every real engine in the Industrial Revolution was paying it. Every power plant today still pays it. The tax did not disappear when we switched from coal to gas to nuclear. Thermodynamics collects regardless of fuel. Steam built the modern world on that tax. Factories, trains, ships crossing oceans in 2 weeks instead of 2 months. All of it was hot water expanding against pistons while cold reservoirs somewhere swallowed the leftovers. Engineers learned to squeeze efficiency without ever reaching 100%. The squeeze is not laziness. It is the same pigeonhole principle wearing steel. You cannot map all the heat into organized work any more than 7 red balls can map uniquely onto 3 blue ones when the law demands unique histories. When Boltzmann later connected entropy to wobble, he was not replacing Carnot. He was explaining him. The waste heat Carnot demanded is energy spread into modes that multiply microstates. The engine cannot recover every joule as organized work because organized work lives in macrostates with smaller w than thermal equilibrium. Carnot's limit is a counting limit dressed as an engineering limit. Notice the asymmetry the course keeps coming back to. First law, delta U equals Q minus W, energy in minus workout, books balanced. Second law, delta S for an isolated system is greater than or equal to 0. Entropy in an isolated box does not balance. It drifts up. You can build a machine that converts work into heat all day. You cannot build one that converts a tank of lukewarm water into a hot side and a cold side without paying elsewhere. Every refrigerator hums proof of that on your kitchen floor. It moves heat uphill, but only because the compressor dumps more entropy out the back than it removes from the inside. The net climb continues. The universe keeps the receipt. One reason physics works as a science is prediction. Given the state of a system now and the equations of motion, we can predict the future. That is determinism. But determinism alone is not enough for an acceptable physical theory. Nature also demands reversibility. The equations must allow you to infer the past from the present, not only the future. A reversible theory means each state has exactly one arrow in and one arrow out, one predecessor, one success. Distinct states stayed distinct. Distinct histories are unique. Without reversibility, Two different pasts could produce the same present, and the same present could fork into ambiguous futures. You could not run a clock backward through the laws. You could not trust conservation derivations built on time symmetry. Quantum mechanics and general relativity both inherited the demand. Statistical mechanics had to satisfy it too, which is exactly why entropy decrease at scale is such a sharp puzzle. The laws pass the reversibility test one collision at a time. The macroscopic world fails the decrease test because there are too many collisions to send back through narrow doors. That may sound obvious at first. It is not, and the consequences are enormous. In plain terms, at every moment you must be able to say what the previous state was and what the next state will be. States that differ now must remain different later. Remember, histories are unique. I will show you with an example. And this is where the second law finally enters the picture. Take 5 colored balls: blue, yellow, green, red, purple. Each ball is a state. Our equation of motion is a rule. From any ball, which ball comes next? Draw arrows between them. First case, blue to yellow, to green, to red, to purple, to blue. Start on blue and you cycle. Reverse the arrows and the rule still works. Every state has one incoming and one outgoing arrow that is deterministic and reversible. Nature allows it. Think of that cycle as a tiny solar system with 5 planets and 1 lane each way. No traffic jams, no merge lanes. If you know where you are, you know where you were and where you will be. Newton's laws for particles work like that in ideal form. One past, one future, no forks. The colored balls are not childish decoration. They are the requirement every fundamental law is supposed to satisfy before we trust it with atoms. You can rearrange the cycle, change which color follows which, and as long as each ball still has exactly 1 arrow in and 1 out, the system stays reversible. Many orders work. The rule is graph structure, not this specific rainbow. Irreversibility begins when 2 arrows try to enter the same state or leave it in a way that makes the past or future ambiguous. Now break it on purpose. From blue go to red, then yellow, then green, then purple. But from purple, go back to red instead of closing to blue. Start on red and ask where you came from. Blue points to red. Purple also points to red. 2 histories hit the same state. Run backward from purple, green, or red. The law cannot decide. Start on blue with arrows reversed, and the next step is ambiguous again. That graph is forbidden. Nature does not accept the deterministic law where histories collide. Real collisions among atoms are reversible in the Newtonian picture. Swap incoming and outgoing velocities, and the movie runs backward. The forbidden graph is not about one collision misbehaving. It is about trying to force a whole crowd of collisions to land on a macro state whose W is too small for the crowd size. The broken rainbow is a cartoon of what cannot happen when 7 trajectories must share 3 doors without sharing a door. Microscopic reversibility survives. Macroscopic decrease dies on the crowded doorstep. At this point, you are probably asking, where is the second law in all of this? Here we mix everything we built so far, and the second law falls out. We keep working with colored balls. 2 sets. The blue set has 3 blue balls, 3 microstates. Call that macrostate the blue ball macrostate. W equals 3. The red set has 7 red balls, 7 microstates. Macrostate the red ball macrostate. W equals 7. By the definition we started with, the red macrostate has higher entropy than the blue macrostate because it has more microstates. Now 2 experiments. Experiment 1. Prepare the system in the blue macrostate. 3 blue balls. Wait, the system evolves to the red macrostate. 7 red balls. Entropy increased. W went from 3 to 7. Check the arrows. Each blue ball can reach a distinct red ball. 7 targets exist. 3 are used. 1 arrow in, 1 arrow out. No collision, no shared histories. Forward motion from low W and reversible laws. Shake hands. As, ands, 2, hands A. This process is allowed. This process is typical. That is what mixing looks like when the graph is honest. 3 ordered stories dissolve into 7 available slots without forcing 2 stories through the same door. Perfume leaving a bottle is experiment 1 with different labels. Dye in water is experiment 1. Even your breath-spreading carbon dioxide in a closed room is experiment 1. Each molecule trajectory adds to a macrostate that was always bigger than the bottle-shaped past you remember. Say it again with the language of arrows. Each blue ball had one arrow out to a red ball. Each occupied red ball has one arrow in. If you reverse the movie, you could follow those arrows backward from red to blue. At least for the 3 reds that were reached, the system told one story forward. It could tell a partial story backward without breaking the graph. Experiment 2. Prepare the system in the red macro state. 7 red balls. Wait the same time. Ask for the blue macro state again. 3 blue balls. Entropy would decrease. 1 would fall from 7 to 3. 7 trajectories must land on 3 slots. By the pigeonhole principle, at least one blue ball receives 2 arrows from 2 different red balls. That is the forbidden collision from the broken graph. 2 arrows into one state. If you stood on that blue ball and asked where you came from, the law would have 2 answers. Partial decrease can happen in tiny systems. 3 reds can return to 3 blues without collision. That is why 43% is not 0. But full return of all 7 to a 3-slot macro state without overlap is the cup rebuilding itself. Every piece needs its own history, and there are not enough distinct histories to go around. The second law is not a ban on ever seeing order. It is a ban on seeing the whole crowd march back into a corner together when the corner is too small to hold the crowd's story separately. Reversibility vetoed the full return. At most 3 of the 7 red microstates can return to 3 distinct blue ones without collision. The other 4 cannot finish the backward movie without 2 histories merging onto one blue ball. Draw the arrows and you will see it. The maximum backward fraction is 3/7, about 43%, not 0. Loschmidt was right that entropy decrease is not forbidden by the equation. Boltzmann was right that it is forbidden by the measure once n is large enough to matter. 43% sounds huge. If that were the real odds, I agree with you. 43% is not negligible in a toy model, but we used 3 and 7 because my editor cannot draw 10 to the 23rd arrows on screen without the render farm catching fire. The logic is exact. The numbers are a cartoon. Compare that cartoon to the coin board for a second. Going from 3 red on a 36 coin grid to all blue is also a decrease in mixing, a walk toward a smaller W macro state. You can calculate that walk. It is allowed on paper. Watch a shuffled grid spontaneously sort itself into a perfect flag pattern, and you will wait forever. The 3 versus 7 balls are the same story with easier arithmetic. Loschmidt asked why the arithmetic of Newton allows backward movies. Boltzmann answered that backward movies are lost in a haystack whose size is W itself. Scale up. A real gas in a box carries roughly 10 to the 23rd particles. The spread-out gas macro state owns almost all of W. The all molecules in one corner macro state owns a sliver. For a decrease large enough to notice with your eyes, the odds are on the order of 1 in 10 followed by 26 zeros. For a full reversal toward a highly ordered corner state, the odds are closer to 1 in 2 raised to the power of 10 to the 23rd. If you showed 1 random microstate per second, you would wait longer than the age of the universe before the air in your room sprinted into a corner and left you in vacuum. Fluctuations do happen in small patches. A few particles briefly bunch up. A microscope can see noise, but the number of particles needed for a human-scale violation grows so fast that waiting for one is not a life plan. Statisticians sometimes say unlikely events happen in large samples. Thermodynamics replies that the sample size here is Avogadro-sized, and the event you want is not one unlikely collision, but a coordinated choir of 10 to the 23rd unlikely collision. The choir does not sing on human time, so for all practical purposes we treat the second law as absolute. The total entropy of an isolated system never decreases with time. That is the second law of thermodynamics. We have never seen it violated at human scales. That is why it is one of the most sacred principles in science. The law is so reliable that it practically governs every everyday phenomenon that seems to happen in only one direction. Let that land with concrete images. Drop a cup on the floor. It shatters. You have never seen the shards leap up, reassemble, and land intact on the table. You have seen the forward movie 10,000 times. You have never seen the reverse. The intact cup owns fewer microstates than the shattered cup. Few ways to be perfect, many ways to be broken. Every shard can sit in slightly different positions. Every crack face can tilt by a fraction of a degree. The macrostate broken cup is a whole family of microstates. The macrostate perfect cup is a needle in that family. Drop enough cups and you always get broken. Not because the laws prefer broken, but because broken is what almost all of W looks like once gravity finishes its job. Hot coffee cools in your kitchen. It does not spontaneously concentrate all its heat into one blazing pixel while the rest of the mug freezes. The lukewarm equilibrium owns more W than a sharp hot-cold split. Heat flow is the system walking toward where the count is larger. Leave milk out on the counter. Bacteria multiply. The smell changes. You call it spoilage. Statistically, it is the same walk. More ways for molecules to arrange into new compounds than to stay in the pristine glass you poured. Perfume in a corner does not stay in a corner. Ink in water does not unmix. Ice in warm tea melts and does not refreeze into a single crystal while the tea boils beside it. Pick any domestic scene, and you are watching W climb. The air in your room does not rush into a corner and leave you in vacuum. Not because the laws forbid molecules from crowding, but because the concentrated air macrostate owns a fraction of W so small you will never live long enough to see it by accident. It is not your friends who left you in vacuum. It is statistics. Friction is the same ledger wearing a different coat. A book sliding across a table slows down. Kinetic energy does not vanish. It becomes thermal motion in the table, the book, and the air. Energy spread into more modes, higher the reverse. Thermal motion in the table organizing itself to push the book across the room is the cup unbreaking again. You feel friction every day. You are feeling entropy accounting in your muscles when you stop a heavy door with your palm. The law governs every everyday process that seems to run in only one direction. Diffusion, friction, mixed and contagion, and any time symbol. Mixing, aging. You could name millions of examples. They all go from a macro state with smaller W to a macro state with larger W. That is how we tell past from future. And that is really beautiful once you see the count behind it. Aging is the slow version of the same story. Your body maintains low W structure, proteins folded, cells partitioned, by spending energy and exporting entropy to the environment. Stop eating and the export stops. Local order collapses because the surrounding world has room for the climb. Life is not a violation of the second law. Life is a temporary eddy that pays rent to the ledger every second. Death is when the rent runs out and the macro states available to a corpse outnumber the macro states available to a walking person by an astronomical factor. Even mixing paint is a ledger entry. Blue and yellow become green, not because green is preferred, but because blended pigments share more ways to scatter light than separated blobs. Stir once and you rarely unstir. The brush has 10 to the 20 something particles on its bristles. The canvas does not care about your intention. It cares about. Joseph Loschmidt challenged Boltzmann in 1876 with exactly this tension. Microscopic laws are reversible. Reverse every molecular velocity at an instant, and the gas retraces its path. Boltzmann's Haidt theorem seemed to prove entropy always increases. Loschmidt showed that reversible mechanics makes decrease possible in principle. The same equations that carry you toward equilibrium can carry you away if you flip the signs. Colleagues piled on. The fight exhausted Boltzmann. He died by suicide on September 5, 1906, near Trieste. The formula on his grave survived. Loschmidt's question survived too. Loschmidt was not playing word games. He was pointing at a real crack between time-symmetric equations and time-asymmetric experience. If every collision can undo itself, why does a smoke ring dissolve and never tighten back into a perfect torus? Boltzmann's reply did not deny the symmetry. It relocated the arrow and Junder. One of tread it put to the stick of the J. Initial conditions matter. A gas starts in a corner of the box and spreads because almost all of phase space is spread-shaped. Reverse the velocities at one instant and you get a corner again. But you had to cheat by selecting that instant from outside the system. Macroscopic movies feel one way because we start from low wobble pasts we can remember and wander into high wobble futures we have not yet seen. Boltzmann's answer is the hinge. The second law is not absolute for tiny systems. It is overwhelmingly probable for large ones. Loschmidt's reversed gas is not impossible. It is improbable. Buried in a fraction of phase space so small that for macroscopic particle numbers the fraction vanishes on any clock humans can read. Boltzmann wrote that the impossibility of an uncompensated decrease of entropy is reduced to an improbability. That sentence ties Carnot's engine tax, our coin grid, and the coffee cooling on your desk into one claim. Macroscopic entropy climbs because almost all of W lives on the high side. Return to the coffee on your desk. The same coffee that justified the logarithm when 2 mugs became 1 pot. It is cooling while you listen. That cooling is not a separate phenomenon from the coin board. It is the board with 10 to the 21st coins. Each coin, a molecule, each flip a way of sharing energy among modes. The mug began in a macrostate with fewer ways to distribute the same total energy than the macrostate it is walking toward. W is climbing. No new force pulls heat out of the coffee. Counting pulls it out. Wrap a sweater around the mug and you slow the climb. You did not repeal the second law. You added insulation. Fewer ways for energy to leave quickly, but the mug and the room still share one combined ledger. Open a window in winter and the house loses heat faster. Same law. Law, different boundary. Entropy of the whole isolated Earth plus room plus sky system still trends up. Humans spend fortunes on boundaries that delay local comfort loss. Thermodynamics always wins the long game. That brings us to the 2 points this course saves for the end, and they follow directly from everything we already built. First, it is remarkable that reversible laws at the atomic level produce macroscopic events that run in only one direction. Every collision can run backward in the equation. Every cup you watch breaks forward because W almost always climbs when particle numbers are large enough. Loschmidt's reversal exists in principle and vanishes in practice for the same reason 3/7 on a whiteboard becomes 1 in 10 to the 26th in a room. Your memory is part of that story. You remember the cup falling. You do not remember the cup unbreaking because your brain is also a physical system whose macro states record past low W events and not future ones. Films can run backward on a screen. Thermodynamics in the room where you sit cannot. The equations do not forbid reverse movie. The measure of initial conditions forbids them for systems big enough to have a past you can narrate. Second, that connection reaches the universe itself. We know the cosmos is expanding. Near the Big Bang, it was dense and hot. Its state had low entropy then. Today, it has much higher entropy, and it still increases every second. There is a deep link between the second law and the arrow of time. The early universe was remarkably uniform, smooth enough that gravity could later build galaxies and stars. That smoothness is a low what do you configuration compared with a clumpy mess of black holes. Roger Penrose has stressed for decades how atypical that beginning was. As space expanded, accessible microstates multiplied. Cosmic entropy climbed, stars formed, stars burn. Black holes stored enormous entropy in their horizons. A star is an entropy factory wearing a pretty mask. Fusion builds heavy nuclei and pours photons into space. Each photon carries energy away from a concentrated core into a dilute sky. Exactly the move from lower W to higher W we saw in the coffee mug. When the star dies, much of its mass can collapse into a black hole. Bekenstein and Hawking showed that black holes carry entropy proportional to their horizon area. A single stellar mass black hole can hold more entropy than all the gas and dust that built it. The universe did not climb toward disorder by accident. It climbed through engines we name with poetry. Main sequence, red giant, supernova, and each engine paid the same tax Carnot described. The cosmic microwave background, light released when the universe was about 380,000 years old, still shows faint ripples that seeded galaxies. Those ripples are tiny next to the uniform glow, which is exactly why structure could grow. Too smooth and nothing happens. Too tackage, too incho, ala fulama hata. Our beginning sat in the window where gravity could sculpt structure while total W still climbed. The universe began in a low entropy state. Reversible laws plus statistics do the rest. Without that starting condition, we could not prefer yesterday over tomorrow. You do not need to accept every cosmological model to feel the weight. Even if you care only about Earth, you inherit a cosmos still equilibrating away from a smooth beginning. As long as total entropy in an isolated system keeps rising, you are watching time move forward. Stars still burn, cups still break. You remember yesterday and not tomorrow because cosmic W was smaller yesterday than it will be tomorrow. Some physicists argue the far future is cold, dark, and nearly empty. Maximum entropy in the bulk with structure only in rare fluctuation. Others stress that gravity makes the story richer than a gas in a box. Either way, the lesson of this course does not change. The same second law that cools your coffee governs the long fade of the sky. We are not outside the ledger. We are entries written while the count still climbs. We should be glad the universe is still increasing its entropy. As long as that happens, we are moving into the future. Time is passing. That is the full story this video set out to tell. Entropy counts microstates. The logarithm makes the count additive when systems combine. Carnot and Clausius measured the climb in engine. Boltzmann and Gibbs explained the climb as probability over collision. Loschmidt proved reverse trajectories exist in principle. Reversibility and the pigeonhole principle explain why they vanish in practice when W is large. Broken cups, cooling coffee, and an expanding cosmos are the same ledger at different scales. If you take one thing from this course chapter, take the count. When someone says entropy is chaos, ask how many microstates they mean. When someone says time flows forward, ask which macrostates own almost all of the microstates. When someone says the universe had a beginning, remember that beginnings with low W are rare and precious. Rare enough that structure and memory can exist while the totals still climb. The formulas will stay on the exam. The count will stay in the kitchen. Entropy is not a ghost and not aesthetic chaos. It is the logarithm of how many microscopic stories match what you see, times a constant small enough to fit on a gravestone in Vienna. The second law says isolated systems wander toward the stories that can be told in the most ways. Thank you very much, and see you in the next video.